Now we are going to move into forecasting, and not only forecasting, but the most difficult kind of forecasting, ramp forecasting. Mohamed, please, over to you.
Good morning. Thank you, dear attending, for joining this session. For the upcoming 12 minutes, we will embark on a journey, and this journey is about wind speed ramp rate prediction. So in this nice strip, we will have 3 steps. The first step is, what is a ramp rate? Second step, why do we even care about it? And third step, what we will do about it. So ramp rate. A ramp rate is a sudden increase or decrease of wind speed. Like we are here, suddenly we increase the power production. Or we are here, and suddenly we decrease the power production. So recently, you have seen an example of this with extreme events like Storm Ciarán, Ingun, and so on. One of the dire effects of this is a turbine collapsing here, and also having blackout events. So when we speak with people that are not in the wind industry, for instance, myself coming from the solar energy industry, when we hear a lot of wind, we imagine people from the wind industry throwing a party. Like, que bueno, que rico, que lindo, Paris, Bilbao. Unfortunately, the truth is a little bit sadder. We look at the technology of the wind turbine. Here, we are producing full speed. And unluckily, we have a wind speed that is way higher than this threshold. And when we go above this threshold that is called the cutoff speed, basically, your production drops to 0. So imagine yourself sprinting and then suddenly coming to a stop. In your body, you will risk to injure yourself. Here, the electricity grid manager, they don't like it. It may cause blackouts. This is an example of what a ramp rate causes. Another cause might be your turbine that is basically completely broken down. We don't want that. So what do we do about it now that we have defined what is a ramp rate and why it is interesting for us? What we do about it is simply try to forecast it, know when it will happen. A nice way to do it is using a weather forecast model. Okay, don't freak out. It's simple. A weather forecast model, basically, it's a box that solves some nasty equation, and at the end, you'll get over a domain the value of temperature, wind speed, and so on. And all the physical phenomena basically are solved within some box that are called physical parameterization. So if we have a set of assumptions, then we will have a different wind speed that is forecasted. So for each scenario, we will have an estimate of the wind speed. Here is a nice animation of what it looks like. Here, it's a nice forecast that was done in Europe. Unfortunately, I did not show Bilbao. I've shown England wind speed evolution over England and wind speed evolution over France. And what is interesting is when we take a deeper look, we can see that the wind speed have some directions. Here, the direction comes from the north to the south. And this is interesting because basically, if we know what happens here north, we have an idea of what will happen here south, maybe 30 minutes after, 10 minutes after, 6 hours after. And the idea is, if you have this source of information, you will likely be able to produce a forecast. And the source of information is called SCADA. Basically, there are devices that are on top of the wind turbine and that measure value of wind speed, relative humidity, temperature, for instance. And what is nice is in Europe, there are a lot of them. But here, I will consider a data set that contains 9 stations. I cannot show the exact location, but here we will have in green the test or the validation site, and that is surrounded in yellow by other wind farms. And this data basically come from Darwin, the NG platform that gathers all the production data from assets. And ideally, we would have the data from all the wind farms around the world. And here is a nice picture. Basically, in Europe, as of 2023, there is 2,500 sources of data points. That's amazing. That's a lot. Basically, everywhere in Europe, we have wind farm. So we have estimate or measurement of wind speed and other quantities. And unfortunately, I don't have access to all of them. What I do is I create a synthetic database. There is observations that are available worldwide. These observations, I treat them manually, and I keep only heights that are those of observed wind turbine. And what do I do about it? Now, I need you to be focused. Imagine this scenario. You are today, you had a huge argument with your relative, your spouse, your girlfriend, and so on. You are sad, and basically what you want to do is to fix the issue. Let's imagine that you have a time travel machine, and this time travel machine is a weather forecast model. This time travel machine allows you to go from today to the day before to launch the simulation, and having the knowledge of today. So you go yesterday, you know that tomorrow you will have a big fight, so you will know what you do to avoid this fight. You understand? So some of you might want to fix this fight with your wife, your spouse, or your loved one. Other one will want to play the winning number of the Euro Million. I don't know who you are. I see some guys that say, okay, yeah, she can be mad, let me have my million. We are not like that. In the wind industry, we are a family-oriented industry, and we want to make things better. Right? So, having this observation, basically what we try to do is to correct the model, and that is this next C equation. The model, having this observation, will be nudged, meaning the observation will tell the model, come here to the right value. And that's called nudging. So let's jump about the result. In this nice animation, basically, I compare my simulation with and without having the SCADA data. As you can see, when I ingest my SCADA data, I reduce my wind speed by 2 meters per second in my domain. Basically, this SCADA data, as my colleague told us earlier, this SCADA data measure the wind speed that is impacted by the wake. That's nice. So basically, the SCADA data allows me to have a modeling of the wake effect. And as you saw earlier, the wind direction takes a direction, the wind direction takes a direction, yeah. It follows the curve. So if I know upstream what's happening, downstream, I can make a forecast. So here is what the forecast look like. I have my real data that is validated in black and a bunch of scenario. Each scenario in dotted dash line are the scenario where we don't have nudging. And all the scenario in plain lines is where we have the nudging. Let's take, for example, the green one. We go from really underestimated it to being more precise. And that's the same thing that we observe. And I will skip it to be quicker. And what we also notice is that the forecast benefits last up to 13 hours ahead. So you can forecast 13 hours ahead the values. Now, let's talk about statistics. We have derived a methodology. We want to know if it's accurate or not. So there are some statistical metrics that was analyzed that are the probability of detection. There is a ramp rate. Does my model detect it or not? The false alarm rate. Does my model tell me, okay, there is a ramp rate and actually there is none? The mean absolute error that says, okay, I have forecasted my ramp rate and I want to know if my magnitude is spot on or completely false. And the time displacement index tells me, okay, does my forecast match actually with the time where it's happening? So this nice table shows basically a comparison for each scenario, the scenario without nudging, E1, E2, E3, and the scenario with nudging, E1N, E2N, E3N, and so on. So we see that the probability detection, we go from 94% to 100%. And to summarize, basically, we now detect every time the ramp rate event that's happening. The false alarm rate, except for the first scenario, basically we decrease the false alarm rate. We are better for detecting the amplitude and for detecting the time. So this method works. So the conclusion basically are, we have our weather forecast, we have a source of data that comes from SCADA, and it allows us to forecast wind power ramp rates. What are the implications? For instance, if you are into trading energy, you will know what you will inject into the network. And in this energy market, basically, if you tell that you will do something, like in life, and you don't do it, you get a penalty. And that's called the imbalance cost. And this imbalance cost, order of magnitude, is millions of euros for a year. So that's why it's needed. And also, a nice thing is by taking several physical phenomena, we have scenario. And this scenario basically are the band that we have here. The spreadest or the thickest the band is, or the widest it is, basically, the more uncertainty there are. The thinner the band is, the more confident we are about the ramp rate forecast. So, really thank you for your attendance and for taking the time to share this journey with me, and thank you.
Thank you very much.
Thank you.